well, some of you got my email message sent out this morning, me lamenting about how to teach this course. It's really hard. It's I hate starting off with these state transition diagrams and all that. Like, as I said, I like geometry. But then I went too far, apparently. So I think that it was really good to go and talk about Lyapunov functions for a nonlinear state space model. But I think the HGB equation scared some of you to death. At least I got that message from some people. And I'll try, I'm keeping a diary, and I'll make a note of that next time. But every time I teach the course, I get a different crowd. But if you're scared, don't be. Like I said in the email, this was basically, in the deterministic continuous case, everything boils down to the fundamental theorem of calculus in a way. And that was the only point I was trying to make. In the stochastic case, you just can't see that as clearly. And so we'll go through that much more slowly. And you'll have lots of time to play around with MATLAB as well. So it'll sink in. So where are we? Okay, so we're looking at finite state space Markov chains. The state I've been denoting x sub t or x of t, and the state space is denoted grand X, which I don't know how to write on a blackboard. And it has a transition matrix. For now, the state spaces consists of m points. They're just integers from 1 to m. Often, we're going to be looking at a queue, and it'll be a buffer size. So we'll have to include 0, 1, 2, 3, 4, up to something. So it'll depend on the context. But we're looking at a time homogeneous Markov chain. I wrote inhomogeneous. I wrote it once and I kept saying it. And I don't know why one of you didn't yell, because many of you caught that I made that goof. But time homogeneous means that this does not depend on time, and we will never look at anything else. We'll never look at an inhomogeneous Markov chain. So this would be called time invariant in the deterministic control context. Okay, so we saw that, and we also saw that if I looked at the probability say xt plus r, so if I looked at r steps in the future, predicting where I'm going to be in r time units, given that I'm starting here at state I at time t, you take the transition matrix, you raise it to the rth power, okay, that's matrix, multiply the matrix by itself r times. You take that matrix and you look at its ij position. Okay, and that we derived that last time. I'll never do it again. All right, I might make you derive it again. It's homework or midterms or something. But this is so basic and it confuses people. How about this? So somebody asked me about this last lecture. Okay, so remember we had our Lyapunov functions before. F could be a Lyapunov function. It could be something like that. Or F could be a cost function. Something that measures the cost to be in a particular state. And we'd like to know what the expected cost will be r time steps in the future, given the time t I'm sitting here in state I. All right? And we all know how, given the conditional probability, how to compute a conditional expectation. At least you should. All right, I'll remind you. There it is. You sum over all possible states j of the probability of being in that state, and then multiply by f of j. It's just how you can compute, just like you can compute a mean. So this is a conditional probability instead of a probability, that's all. And this is how you would compute the mean of a function of a random variable, right? No, this is a definition of a conditional mean. You know?
Oh, I see.
Yeah. You're definitely right that I'm about to get to that, for sure. But this, this has a conditional distribution, which was given right there. And I look at the conditional probability of being a state j, multiplied by f of j and sum over all j. That is the definition, if you like, of the conditional expectation. And what we just saw, as you were pointing out, you're one step ahead of me, that this is equal to this. And I'm going to keep writing it like that, just to make sure we don't get confused. I mean, but that's really cumbersome. You can see why in a linear algebra course you would never write it like that, You write, in a linear algebra, when you learn about matrices, and that R doesn't look like an R. You assume that nobody's so silly as to take p sub ij and take it to the rth power, even though people make the mistake in simple, when they introduce to matrices all the time. It's just that people get confused when they take this course because it's such another world. They make these silly mistakes. But note, this is matrix vector multiplication. Matrix vector multiplication. I said f's a function, but we're going to interpret it as a vector. And you're all going to make mistakes and get upset with me. But damn it, this is PF. P to the RF, matrix vector multiplication. And then evaluated at I. I don't want to have to keep writing that over and over again. It's ridiculous. When you take courses where they involve matrices, they don't do this every time. They say, look, it's shorthand. Okay? Now, believe it or not, this is the biggest sticking point I get in when I teach this course. This is the biggest thing. And it's sort of like if I was teaching arithmetic and you refuse to learn the plus sign. You have to absorb this notation, or we'll all get stuck and we'll never get anywhere. But I get such pushback. So transition matrices, these transition probabilities are matrices, and functions are vectors. And it's perfectly reasonable when the state space is 1 through m, because I think of f as a vector. So I associate a function with just the vector it induces. And P is, of course, is by a matrix. Then you can see I get matrix vector multiplication. Yeah. But I know half of you are going to, tomorrow, next time we talk, what the hell are you talking about? And 1 or 2 of you won't know what I'm talking about even in April, and then you're dead, because you can't imagine how often we're going to need this. These dynamic programming equations, I couldn't even talk about them if I had to write this out all the time. You know, I just couldn't work. You know, and all this, you know, some of you want to learn about Q-learning, reinforcement learning. We'll give up if we don't have this compact notation. Yeah.
So if we're not looking at a finite state space, how are we interpreting it?
The same thing. So when I gave you that was part of the reason I brought that generator notation. We already talked about mappings from functions to functions. So basically, recall I define df of x to be equal to the derivative with respect to time of f of xt given t equals 0 and with x0 equals x. So we've already talked about abstract operators that take a function and give you a new function through some crazy mechanism. And it's totally analogous. Yeah. So it's a mapping from functions to functions and a linear mapping. So this is you know, if I take you know, instead of f, I have a sum of two functions. You know, df plus g is df plus dg. And you know, it's a linear mapping, just like matrix multiplication is a linear operation. Yeah, we'll see, because we'll need it for countable state spaces.
But
and
if it's not a finite dimensional state space, how do you? I still don't understand. How do you?
I'll show you. We'll do it today. We have a longer lecture today. I'll give you an example. I'll give you an example in a bit. Yeah.
About that notation right there. Are you evaluating at x equals t or t equals 0, or you just?
Yeah. So what I do is there was a. Oh wait, F was the dynamics. Shit. I can't use F. F was the dynamics. I can't use that. Terrible. Put a V here. Damn, forget it. Go. I don't want to waste my time here, because F was this was for the model x dot equals f of x. So it's terrible to have F's used in different contexts. But go back in the notes. We used the chain rule to say that this was the gradient of v dotted with the dynamics. Yeah. So that was what we did last week. Okay. But yeah. I gotta erase this. This is going to confuse us. Yeah. So I'll give you an example to address your question. Yeah. All right. So. So I gave you a homework assignment to get you ready for this lecture in a way, so you can think about it in advance. And part of the reason I felt, you know, it was valid to ask you for an eigenvector was because you were playing within the homework. But yeah, don't worry about it. I know most of you did it last night. We saw that we could solve So we saw last time that I can solve this eigenvector equation with the eigenvalue lambda equals 1 and v of I equal to, you know, well, a constant, you know. You know, so in this correspondence, v corresponds to v0 dot 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 v0. Right. And all we're doing is saying All we're saying is that the sum over all j of pij is the probability of going from state I to somewhere, and that's 1. I'm always going to end up at some state j, because for each I, this is a probability mass function. It's a distribution on the state space. Okay. So there's always this eigenvector, and there's also a left eigenvector, which you worked out in the homework for one example. So when we multiply in the left, I'm going to typically think about row vectors. So pi here is going to be a row vector. We wouldn't like that, okay? And so how do we interpret this, okay? And we interpret this probabilistically, and some of you have seen this and remember it, and some of you don't at all. Okay, so I'll just review it. What does this mean? Suppose I can assume that pi is a probability mass function. That means that the elements are non-negative, and that they sum to 1. So that's a leap of faith. Maybe it's not possible. But suppose I could do it. And suppose then that x0 is distributed according to pi. I can then ask, what's the distribution of x1? And we'll see it's pi. Okay. So we play the same game that we've played before. We use Bayes' rule. So the probability that x1 equals j is the summation over all I of the joint probability, because x0 had to be something, right? Okay. This is an event, the event that x1 equals j. I'm just saying that that event is the union of these events. And I'm using the property of probabilities. Right? That's why you need to have taken a probability course before taking this course. And then I use Bayes' rule. And I see that my transition matrix pops in, and I see that my pi pops in, because this is pi of I. And that is multiplication on the left. That's what I mean by pi times p, okay? You all know the definition of a row vector times a matrix. It's exactly that. So that's what I'm saying is pi of j. Okay, so a big part of studying Markov chains is often getting properties of this invariant probability mass function. Does it exist, and what properties does it have? And it's just a compactification of the problem. Is that basically what we're going to find out is this. In the unit chain case, we find that there's a single eigenvalue at 1, and all the rest are strictly inside the unit circle. And I wish I had drawn, I'll put it here. Where's the, oh, no color. Let's put one there. Very often it's assumed that there's a second eigenvalue, which is the one that's closest to the unit circle. You know, and so I made you play around with that in the homework. And we find that if you look at p to the t, and you go from I to j, in the unit chain case, this finite state space case, this converges as t goes to infinity to a rank 1 matrix And what do I mean by that? So I said pi was a row vector. What's v? I'd have to think about this. This had better be a transition matrix, because this is a transition matrix for each t, and so it's got to converge for transition matrix. And it turns out the only way for that to happen is that v is a vector of all ones. So pi is the left eigenvector, and v is the right eigenvector, but normalized, so this is a transition matrix. All right, and that's a bit of linear algebra. You know, you can actually just, you don't need to do anything with probability. When you have an isolated eigenvalue like that, basically what this is saying is you, oh, I don't know. I mean, it's a standard trick is that you do a decomposition of the matrix to get results like this. So if you take a mathematical control course with state space control course, you'll cover this in the first few weeks. I know you haven't. Don't worry about it. And actually, I'm not really going to prove this. You know, maybe I'll do it through examples and things like that. But you know, because we have too many things to do. What I want to say. So, what about other eigenvalues? Just for the fun of it. Okay, so this v, maybe I should put a star there, put a 1 there if you like. But I want to look at all sorts of eigenvectors. So suppose that I could solve this equation, PV equals lambda 2v, where lambda 2 is the second eigenvalue. Right? It'll give us some intuition about this, what I'm claiming about the rates. We all know we could do this. I'll do it. What's p to the RV? Forget it, I'll do it. If I look at p squared v, it's p times pv, which is p times lambda 2v. Lambda 2 is a scalar, comes out, and so forth. Okay, so we get that. That's saying something, and so basically we know that since this is strictly within the unit circle, this does go to 0, and you can see the rate is lambda 2 to the r, which, you know, so I'm looking at just one vector. You know, this is saying for all I and j, the convergence rate is lambda 2 to the t. Here it's to the t, here it's to the r. You can make that a T if you want. But this is a sum. Just to remind you. So here I don't have a sum. I have just, for each I and j, this converges to this rank 1 matrix. This is just a matrix where all the rows are equal to pi. That's all I'm saying. It's a column vector and a row vector. So it's just a matrix with all the rows equal and equal to pi. Right? But this is a weaker result. It says that for eigenvectors, I take this and it converges to this, which goes to 0. Right? And so you can do an eigenvector decomposition. And so people study this because they want to know how long does it take for a process to basically be stationary, you know? And so how long does it take to forget the initial condition? It's, you know, it's the question you need if you want to simulate. How long do you have to wait? Okay. All right. Anything else you want to say there? All clear? Yeah.
It's just that, so the bigger the lambda 2, the slower the process becomes. Like the slower the...
Yeah, absolutely. So that's right. That's right. So I mean, you'd really, you know, if you want to pretend the process is stationary, you'd like a lambda 2, which is far from, you know, far away from the unit circle. And I shouldn't have said unit. I should have said unit chain. What did I forget in this diagram? Notice I have no poles on the, no eigenvalues on the unit circle. I forgot to say aperiodic. If you have, when you have periodicity, you end up with eigenvalues on the unit circle. And I don't think I'll prove that to you, but maybe I'll get you to do it for me. Unless there's a question. Can I kill this? No? Okay, so here's the state. So I told you the state space is 1, 2, 3, 4. Sometimes it's easier to visualize things in 2 dimensions. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 states, but they're clustered. And so basically, from here, I end up with one of those with probability 1. You know, and from here, I hop to here with probability 1. So I just go from here to here to here. So this is a Markov chain with period 3. And again, what I mean is, for example, the probability that, well, the sum of a j in x1, pi to j, is equal to 1 if I is in x0. That's what I mean by this. You see? That's what we mean when we say Markov chain is periodic. It has a decomposition like this. All right. So in 3 steps, I come back to where I started. And in 3 more steps, I come back to where I started. 3 more steps, I come back to where I started. So if the Markov chain sampled every 3 time instances is not irreducible in any sense because you're isolated, you're stuck here. You know, so periodicity has something to do with irreducibility. You know. Right? So can anybody find an eigenvector for me that's sort of fun, you know, like I talked about on the unit circle? Any guesses? Eigenvalue. Well, yeah. First of all, let's guess what an first, let's guess where an eigenvalue would be, and then let's try to find the eigenvector, just for the fun of it. So here's the real Here's the imaginary axis. Here's the real axis. We always know that there's always going to be an eigenvalue at 1, always. It's a transition matrix, period. Yeah.
It's got to rotate around 3 times to get back to the same
Yeah.
spot, so it's like 100.
Yeah. I'm with you. Yeah. So that's pi, so 2 pi over 3. You know, or 120 degrees.
Yeah.
Yeah. Yeah. Okay, you got it. So are you on the hook for the eigenvector? No, Neil, you're on the hook for an eigenvector. Well, hint, I put this in, well, actually, I should put a j there. That point there, no, I should e to the e. I got that right. 2, yeah. Yes. So that point there, that eigenvalue is e to the 2 pi over 3j. You know? And a hint, the eigenvector will be constant on each of these components. And so you can kind of guess. Come on, guess. What's that? Well, it's constant in each component. You know, and if it's constant in each component, I could always normalize so it's 1 here. You know. Yeah, what's that? I'm not even sure. Yeah. So, here's a conjecture which I will let you come up with. I've got it in my notes, but I think it's more fun just to tell you what I think I remember it being. V of I is equal to something like that in set I. And I shouldn't put an I should put a k, because I looks too much like the square root of -1. For anybody, any math people in the audience. So that times k times j, if, I'm sorry. Sorry. Stop, everybody. So I'll put an n here, because this has to be different. I'm saying it's constant here. Okay. That's what I was trying to say. So I've normalized things so if I'm in the first set, you know, k equals 0, then I get the exponential of 0 is 1. And if I'm in this next set, k equals 1, and I get this eigenvalue. And it's possible I have a sign error. I have to put a minus sign there, but I'll let you do it. Yeah, but I think you will find out. I'll make you do it, that PV equals lambda V. Okay, so I'll give it to you in the homework. And so you see this, you know, I mean, there's a perfect connection between all the things you might have learned about in a control course where eigenvalues were so important and what happens in Markov chains. All right. Well, I have the answer here, and I may or may not be right. I'm not going to tell you. I've got to put it in the homework. I'll let you work out yourselves. It'll be better. Joel? Yeah. Okay. But one of the most important conclusions, though, is we don't get convergence. I mean, if you look at p to the tv, we just said that's equal to lambda to the t v. And lambda to the t is just, you know, doesn't go to 0. You know, it just oscillates around. You know, and we don't want that. We don't want that. We'll see. We do not want that. All right. So let's go through some examples. But unfortunately, no interesting example is in a finite state space. So even though I've been talking about a finite state space, and I had here 11 states, you know, we're stuck. We have to look at something more interesting than that. Yeah, and really, all the spectral theory really does still play a role. It's just we can't compute things typically. You know, we can only get bounds. Okay, shall we? All right. Before I do, I mean, let me just make one important statement, which I'll make a million times. So recall that, I think Anand, you made this point, and I made it when I came in, that almost always the realizations of Markov chains that we look at, finite state space or not, can be written in this recursive form, that the new state is a function of the old state and IID noise. So we've got this nonlinear stochastic recursion, and then we're using linear systems theory to analyze it. You know, that's one of the big reasons we look at Markov chains. You know, basically, you know, taking something horrendously nonlinear stochastic and then using linear systems theory to analyze it is pretty remarkable. And this is even true not in a finite state space. The linear systems theory is the key to all this.
We're able to apply linear systems theory because P doesn't depend on our state.
P depends on state. Doesn't P is
like, I mean, it's like, I don't know, it's not changing something.
Well, it's a time homogeneous Markov chain. If it was time inhomogeneous, sorry for my error last time, then the theory would be pretty, it would still be linear. We still have a linear theory, but the theory of linear time variant systems is not as pretty. Oh, that's all. Yeah. Did I answer your question? You know, if P
between the dynamics and the Markov chain, I suppose.
What's that?
Because like one is like we're talking about probabilities, and the other one is like the actual dynamic. How do I get from one to the other? I need an expression for F. How would I just arrive at it?
Well, I mean, we did that last time. So if, you know, basically in this case, the probability that in the finite state space case, so probably xt plus 1 equals j, given xt equals I, well, xt is I, and that's independent of x. Yeah, so first you have to construct this matrix, compute the probability that f of I wrote n of 1, I could have written n of 2. This distribution doesn't depend on time. You have to compute this for every I and j. And then you get your transition matrix, and you've got linear systems theory. The big thing is this lifting. We start out with just m points, maybe 11 points. And then we have to go to R11, which is uncountable. So we go from 11 points to an uncountable 11-dimensional Euclidean point. It's that explosion in size that allows us to get something linear. You know, and I've mentioned, some of you have heard me say this before, but that's a theme in optimization, is you make a problem way more complex and make it simpler. You know, raise the dimension and you make things linear. It comes up all the time. And this is one of the nicest examples of it. Okay, so I'm going to go back and forth throughout the course. I'm going to go to finite state spaces if I actually want to prove anything, and then go to a general state space and just play around you know, and most of the time we can't prove anything because it's too technical, but you can, you know, you just have to believe me. So it's faith-based education, okay, which is, I think, very fitting given that tomorrow, you know. Sorry. I'm not supposed to say that, but it's okay. All right. Let's see. What do I want to? Yeah, let's go to the. So I'm really pretty much following the notes now. The first notes. Okay, if you look at the notes, it's a linear state space model. Okay, I won't spell it out. You can see the notes. And what I mean by that, there's a so now the state space is not finite. It's actually all of Rn, you know, but it's a linear system. Okay, so this is it's a classic linear system you'd see in a control course. All I've done is I've added a disturbance, and you know, I mean, let's take it one-dimensional. Just for the hell of it, you know, it doesn't have to be, but you know, so that would mean that G is a column vector. So G would be an n by 1 column vector. And F would be an n by n matrix, okay? So you've got a column vector here multiplied by the noise. Again, it's not important. It could, this could also be an n by n matrix, in which case n would be a n-dimensional random sequence, right? Now we can't talk about transition matrices, we talk about transition kernel. And I mentioned this before, that that's the terminology you'll see. So I'll talk about the probability that in one step I'm in some set. You know, O could be some ball or a box or some, or an interval, a point, whatever you like. And if x of t is x, then xt plus 1 is just fx plus the noise. All right, and I chose 62 just to emphasize it doesn't matter what I put as an index. The distribution of, you know, n1, n2, whatever you want is the same. All right? And so, you know, this is fairly complicated unless you put some assumptions on n. And that's why you typically will assume n is Gaussian, typically. Yeah. So if okay, so if we want to go any further, if we actually, so if this is too abstract, right? I mean, all of you are going, what the hell, you know? If we assume it's Gaussian, then we've got sums of Gaussian random variables, and everything gets much simpler. All right, so let's go and play with this. So, you know, let's go through, and we were looking at the long time behavior of the process before for finite states Markov chain. Let's do the same thing for this model. And so 1 is not very long time, so let's go to 2. All right, and then substitute in again. You know, so take the expression for x1 there and plug it in. And you can imagine we can keep doing this. All right, I can go in and now. Oh, I'm sorry. Where's the typo? There's a typo somewhere. Yeah.
On the bottom line, on the right-hand side.
Excuse me.
Right there.
Okay, and I can look at x3, reject, and we don't have to do any thinking now. We can just guess that this is f cubed times x0, and plus we're going to always yeah. You all should tell me. Think so? Yeah, I'm going to multiply this by f, so it'll be at n2. And we're always going to get a g times n3 there. So now we can do the pattern recognition, that there's a gn3 with an x3, a gn2 with an x2. So we got the tail there, and we know there's a convolution formula. Okay, so hopefully you've seen that convolution formula before. You get that xt is equal to f to the t x0 plus a sum, and it looks like k equals 0 to something of f to the t minus k. Oh, no, it's not quite right. We'll get to it.
And k plus 1.
Yeah.
Start k plus k1, start k from 1.
I think I'll go with that. Yeah. Yep, thank you very much. So as long as it's true at the endpoints, as long as you check it for k equals 1 and k equals t and see if you get those terms, then that's right. So anyway, it's a convolution formula you can work out. And so you can see there's an ergodic theorem that somehow this is steady state behavior. But that's a horrible way to look at it because of the fact that this shuffling around of this convolution formula, this thing does not settle down. It just bounces around all over the place. But we can use the fact that nk is IID to write this in a way where we do get something more understandable. So this has the same distribution in distribution. So the nKs are Gaussian, they're IID, and you take a linear combination of Gaussian random variables, you get a new Gaussian random variable. We know the mean of this is 0, because I've assumed that these guys have mean 0 and variance 1. Okay? Now, when I do this fooling around, these are still independent random variables that are mean 0 and variance 1. So the Gaussian distribution of this and the Gaussian distribution of this are identical. And I never need the fact that they're Gaussian, by the way. Just the fact that they're independent and identically distributed. So this is a kind of trick that's used all the time in Markov chain analysis. It's sort of using the fact, in information theory too, to sort of using exchangeability, to be able to get something more tractable. All right.
Is that any part of what's like defined or?
Oh, D is in the same distribution is what I meant. Yeah, yeah, thank you. That D looks like define, but I mean, yeah, distribution. So, so let's go back to here. What's
reverse the direction? You mixed around the noise values?
Well, the thing is that they only have the same distribution, you see? I mean, you know this is a Gaussian random variable, and you can compute its covariance, you know? And in fact, we should say that. So, so what we've said here is that xt has a Gaussian, is a Gaussian random variable whose mean is given by ft times x0. You know, let's just emphasize that I start at some deterministic value, some vector in Rn. And some covariance, which I can't fit in there, but it's the covariance of this. So it's actually, this is IID, zero mean. What you find is it's the covariance matrix is just a summation from 1 to t ft minus k. I don't like that though. Forget that. You know, let's make a change of variable at this point. Remember I wanted to go from 0 to t minus 1. I want to do it now. So let's make a change of variable and call it t minus k. Let's give it a different letter if you like. Call it n if you, I mean m. Okay, so in that case, if I look at the expectation of this squared, if you like, this times its transpose. So remember, the covariance of a random variable is you center it, you take it, you subtract off its mean, you know, and you look at that times its transpose, and you take the expectation. By subtracting off the mean, all I do is I get rid of this term, that's the mean, because the mean of this is 0. And you look at the expectation of this times its transpose, I just get the sum of this times its transpose. I'll let you do that. Okay. So somebody in state space control, anybody who's taken state space control, tell me what you call that thing. There's a name for it, right?
Some kind of Graham.
Yeah, the controllability Grahamian. Not quite though. So So under some conditions, which I'll ask one of you to make precise, this distribution converges to a final Gaussian distribution. Can you see that? So I want this as t goes to infinity to converge to some steady state distribution. You know, well, that's going to have to go to 0, right? We want, I mean, in order for things to make sense, I want f to the m to vanish. So we're going to have, that's a stability assumption. So this will be 0, and this will be the sum from 0 to infinity. Again, provided the eigenvalues of f are strictly within the unit circle. And we even have a realization of the ergodic limit. You know, basically, if I ran out of room. If I look at the expectation of any, I'm going to assume continuity. You'll see why later. And let's assume it's bounded so I don't have to worry about anything. If I look at the mean of g of xt, it's exactly the same as the mean of this funky thing. And, you know, these guys are the same in distribution, means that I can take the expectation of this instead of the expectation of this. So I can actually write down, there it is, that thing has the law of the steady state. And I can write down, you know, my limit in that way. But I do need continuity, and the reason for that is that this thing, oh, I deleted it. Yeah, this thing goes to 0, and it may be that it matters. I'm giving you a homework problem so you can see that. And maybe I'll go through and just draw a sketch on the blackboard to give you some intuition. Yeah. In general, I need continuity. But that is what you said. So sigma is you know, I'll get rid of it here. Sigma So if you take a control course, you know, you're going to study this controllability gradient. And if you think of this as a control, controllability gradient has a lot of importance. Do you remember why?
I mean, it's like what allows you to guarantee your ability to transit state to state.
Exactly.
Under that control analysis.
So if sigma is positive definite, so it's always positive semi-definite because it's in this case it's a vector times a vector transpose. So each term is positive semi-definite. You take the sum, you get something positive semi-definite, but it could have 0 eigenvalues. If it's strictly positive definite, that first of all is equivalent to this limiting Gaussian distribution of a density.